So, this is part 2 of our discussion on the basic properties of nuclei. So, let me just remind you what some of these basic properties are and what we will discuss shortly, namely the mass of the nucleus, which of course, once you have the binding energy, you can compute the mass. You know the mass of the ingredients, mass of the proton, neutron. Then the spin and parity of a nucleus, so is denoted often by J, J for spin, pi for parity. And it is also true that the maximum angular momentum that a nucleus can hold is of the order of about 80 units of h cross. And this is so for nuclei with A of the order of 120. For lighter or heavier nuclei, this number goes down. For instance, for the lightest nuclei, you can't have stable nuclei with lifetimes much greater than the strong interaction time scale of the order of 5 or 10, whereas, and that's the same even for very heavy nuclei like A equal to 250 and so on. There again, the angular momentum that you can carry is only about 10 or 20 units of h cross. The excitation energy, of course, you have ground state of the nucleus, but if you go to higher and higher excitation, initially you have discrete states up to about a few MeV, and then once you cross the neutron or proton emission threshold, which for stable nuclei is of the order of about 8 MeV or so, then you start emitting particles. Then you have states whose width starts increasing, becomes keV to tens or hundreds of keV and then even MeV. And so on, and so then you have also the number of levels increases per unit energy interval. And if you go up still further in excitation energy, then the nucleus cannot have excitation energy beyond about 4 to 500 MeV for about A equal to 120. At that place, everything just breaks up, the nucleus just breaks up. The typical lifetimes, or alternatively the widths that can be calculated from the lifetime. So, the lifetimes are of the order of 10 to the minus 20 to 23 seconds for a hot compound nucleus, and of course, for ground states of certain nuclei, so the most stable nuclei, this but still which decay, this can be as long as 10 to the power of 24 years. Year, you might remember, is of the order of a few times 10 to the 7 seconds. Okay, so isospin is also a good quantum number. So, the ground state isospin is usually in nuclear physics denoted by n minus z by 2. In nuclear physics, of course, the Tz is half of n minus z, whereas in particle physics you use z minus n. So, a proton has plus half in particle physics, whereas the proton has minus half Tz in nuclear physics. That is just a matter of convention. Then you have the electromagnetic moments, you have the diagonal magnetic dipole moment, then you have the electric quadrupole moment, and then there are of course transition moments, both magnetic type and electric type. You also have density distributions of charge and matter. We have mainly discussed electron scattering, or we will discuss in next talk. But you can also get matter distributions through hadron scattering, which is sensitive to the neutron and proton distribution, not just to the proton distribution. Okay, so from the masses of nuclei, this has been going on since last 60, 70 years, or even somewhat more than that. There is an empirical formula which has been developed for the binding energy of nuclei, which is good to within a few MeV. So, the binding energy has a volume term which is given by the constant AV times the A. Then there is a surface term, and that happens because the nucleons that are on the surface do not have nucleons beyond that, and so you have to correct for that by putting a surface term As times A to the 2/3. So, A to the 2/3 is something which is proportional to the nuclear surface area. And then there is a Coulomb term AC times Z squared by A to the 1/3, which is proportional to the radius of the nucleus. Then you have a pairing term. So, nuclei which have a pair of nucleons, the outermost nucleons, you have a pair, they have slightly more binding energy than the ones which have an unpaired nucleon, and so that is given by this delta pair and by square root of A. Similarly, because of course this depends on only the outermost nucleons which are near the Fermi surface. Then there is an asymmetry term which that part of the energy is proportional to n minus z squared by a. So, either if you have more neutrons or more protons, then this binding energy is somewhat less than the one for the symmetric case. And so, I think there is a typo here. This should have been probably minus. Okay, and so the constants are given here. So, I think I'll have to check this. I think this is so the pairing term is positive, so it contributes positively to the binding energy for even neutrons and protons. It is 0 for odd A, and indeed if you have odd Z and odd N, then this is a negative term which contributes to the binding energy. Okay. So, then we come to how do you measure and assign spin and parity of a nucleus. So, this is usually done by transitions to and from that state by looking at beta decays, gamma decays and so on, but also by looking at the hyperfine splitting of atomic transitions. For instance, if you have a transition where you can look at the final state and that final state is not split, then it has a 0 spin. On the other hand, if that final state has a spin half, then it will be split into 2 levels or more if the spin is higher, like 1, 3 half and so on. This splitting of course can be measured only for long-lived state with mean lives order of greater than milliseconds. If it is shorter than that, then of course you can't use, it's difficult to use atomic spectroscopy. You would have to use other methods like beta gamma decay. How do you measure the excitation energy? Well, you look at the low-lying states, you look at gamma decay and you can measure the gamma ray energies very precisely. So, you can measure the excitation energy very precisely. You can also look at particle spectroscopy. If that happens to be above the particle emission threshold, then you can look at the particle spectroscopy, or you can do reactions where you have charged particles in both the initial and final states, and you can measure those very precisely using magnetic spectrographs. And of course, the incoming energy you know from a accelerated beam, if it's a DC accelerator, you know that energy very precisely to the order of a couple of keV. And similarly, spectroscopy, if you have a final state particle coming out, you can know that energy to again within a few keV or at least 10 keV of that order. So, that way you can measure the excitation energy. High-lying states, of course, then you have to look at resonances, which are some of these resonances are beyond the particle emission threshold. So, you can either measure spectra of the particles, you can characterize the reaction by measuring the evaporation residues from compound nuclear decay and so on. Now, of course, when it comes to measuring lifetimes which are long, then you use the radioactive decay law, dN by dt equal to minus lambda n, where n of t is n0 times e to the minus t by tau. So, if you measure the time dependence, you can extract the lifetime of the state. So, long lifetimes are measured by looking at decays in a known interval of time, and then you from the slope of that curve dN by dt is equal to minus lambda n. So, from there you can extract lambda. Now, this works for lifetimes up to about 100 years or so, because of course, if they are longer than that, then you have to use the fact that I have to measure dN by dt, I should know n and then I can extract tau. Whereas, if the lifetime is shorter, as I said, of the order of 100 or less years, then you can actually just measure the count rate which is changing with time. If the half-life is much longer, then it does not change with time. So, there what you have to do is you have to measure the number of atoms which is decaying and how many atoms you have to start with, because that rate will, the decay rate will be more or less constant. It will be very difficult to measure the change in that decay rate. Shorter lifetimes than typically of the order of minutes or so, you can measure by measuring the decay as a function of time by using fast electronics. And of course, you have to also have fast detectors. So you have to have, if you are using a scintillation detector, that has to be a fast scintillation detector and so on. And there you can measure lifetimes even using centroid methods or the decay curve of the order of about 10 picoseconds or larger. If it is shorter than that, up to about few times 10 to the minus 15 seconds, then you can use the Doppler shift method for transitions, gamma ray transitions from recoiling excited nuclei. For even shorter lifetimes, sometimes it is possible to use the K-X-ray method, whereby you can measure the target X-ray intensity and also the target and compound nuclear in combination. So, the compound nuclear X-ray intensity, because suppose you form a compound nucleus and there is a hole in the there is a K vacancy, then it can fill up. But if that filling up happens after the compound nuclear decays, then of course you only get back the K-X-ray corresponding to the daughter nuclei that are produced. So, this way you can measure lifetimes of the order of 10 to the minus 16 seconds, which is the order of a K vacancy filling lifetime. You can also measure the lifetimes of shorter nuclei in the range of 10 to the minus 17, 10 to the minus 18 seconds by using channeling in single crystals, because if that decays on a very short time scale, then these particles can get channeled in certain directions in a single crystal. Whereas if it is much shorter, then of course it's much more difficult to measure this channeling. So, if the lifetime is lesser than about 10 to the minus 17 or even 10 to the minus 16 seconds, then it might sometimes be possible to measure the energy width of the state or the resonance. And then you can use the mean life width relationship, namely tau is h cross by gamma, where gamma is the width, and this is the constant 6 10 to the minus 16 eV second by gamma. That way you can measure the lifetime. And actually, for instance, the lifetime of the beryllium-8 ground state is of the order of about 10 to the minus 16 seconds, because it has a width of the order of 6 electron volts or so, and that has been experimentally measured. So, there you experimentally measure the width of the state and then you infer the lifetime. For of course, for states or in the continuum, then you can only get an average lifetime, and so you can look at the energy dependence of fluctuating cross sections, because you have overlapping states. So, in a limited domain where you have fluctuations in the cross section in the continuum, you can infer what is the average lifetime even if you do not have a resonance. Okay. So, that's for very short lifetimes. The isospin of a particular state can be assigned again through decays, gamma decay, beta decay, particle channels and so on, and also from the systematics of the isobaric analog states. So, for instance, I already discussed this to some extent earlier in an earlier lecture. There is a 15.1 MeV 1 plus state in carbon 12 that does not decay to alpha plus beryllium 8, although it is well above the threshold. So, it in fact decays by photon emission, and so there you about 90% of that decay width it comes from photon decay, and that is because it does not decay by to alpha plus beryllium 8, because of course there is isospin forbiddenness, but there is also angular momentum hindrance, okay, because that kind of decay would have required L equal to 2, and that is difficult to get. It will be very hindered. The electromagnetic moments, for instance, the magnetic dipole moment can be measured, as I already said some time ago, through the nuclear magnetic resonance if it has a spin not equal to 0. You can also look at it, the hyperfine splitting in atomic spectra, or you can, if the nucleus is beta decaying, you can look at beta decay NMR kind of experiments which do the NMR in coincidence with the beta particles that come out in beta decay. You can also look at Larmor spin rotation in an external magnetic field. So, if the lifetime is large enough, I mean even as short as 10 nanoseconds or greater, then you can actually this excited state can be made to the spin of that excited state can be made to precess in a external magnetic field, and from that Larmor precession frequency you can infer the magnetic dipole moment. This is in fact a very popular technique which is used in nuclear physics. A similar technique can be also used for measuring the electric quadrupole moment. So, this also affects the fine structure of atomic states. Also, you can have a precession in a external or even an internal electric field. Usually, it is internal electric field, because if you have a non-symmetric crystal where you have a gradient to the electric field, then this excited nuclear state, if it has a finite electric quadrupole moment, the angular distribution will change as a function of time, and from that you can infer the electric quadrupole moment. The electric charge and I should say matter distribution we will discuss later, that can be inferred from atomic spectroscopy in the following way. All the S atomic states have an electronic wave function which is closest to the nucleus, okay, and that is affected most by the finite charge distribution in a nucleus and the magnetic moment of the nucleus. So, the isotope shift for a 1s electron from the effect of a finite sized nucleus of radius r and charge Ze, let us assume it for the time being to be uniformly distributed over up to a radius of r, then relative to a point charge particle, this shift is actually proportional to, of course, the wave function of the electron at the nuclear site squared, but also to the r nucleus squared. Okay. So, if you can compute what it should be for a point charge particle, then you can, from experiment, you can infer what the r squared for that nucleus is. So, in general, the delta E is proportional to root mean square or not root mean square, the mean square radius of the nucleus. Okay. Of course, it is also proportional to Z, because that is the total amount of charge there. So, for a 1s state in hydrogen, for instance, this can be computed, and you can see what this relative shift should be. Now, this becomes larger if you have a muonic atom, because as I said, the muonic atom is 200 times smaller. So, the wave function of the muon at the nuclear site is much more, and therefore, you can get this shift, which is fairly large in the case of a muonic atom. Then you can also compare what the shifts are for different isotopes of a nucleus, and it also is interesting that the absolute shift is hard to calculate, but a relative shift is easier to compare with theory. Now, this isotope shift not only comes from the difference in charge distribution or finite charge distribution, but also from the mass. So, different isotopes have a different reduced mass, and so that also contributes to this shift, and that can be measured, and therefore, you can say what this mass shift is and what the shift because of the charge distribution is. The mass shift is much more than the field shift for light nuclei, but much less than the field shift for heavy nuclei. Now, the isotope shift, of course, is measured through one of the most the nicest ways of measuring this is through collinear laser spectroscopy. This was pioneered at Isolde, CERN by Professor Otten, who was at Mainz at that time. The principle is that if you have a laser absorption by a fast moving beam whose kinetic energy is half just non-relativistic, so it is half mv squared, then the spread in that energy is just given by mv times delta v. And so, if you invert this delta v, which actually relates to the Doppler width that you would get when you do an absorption experiment, then this delta V remains constant even as the ions are accelerated. The energy spread remains constant. So the Doppler spread which is there, that comes down like 1 by V, especially at 0 degrees or 180 degrees. And this is the reference where this was first pointed out by Kaufman. And so you can take a beam accelerated so that it is fast moving, and the energy width remains the same even through the acceleration process. So that's decided more by the not so much by the acceleration process, but by the ion source spread in energy. And so you can make that the velocity spread a small fraction of the total velocity, and then you can do this collinear laser spectroscopy. So this is a typical setup from this paper, Notterheiser in 2008, and you have a dye laser where you can double the frequency, for instance, and then stabilize it and so on, and then you shoot it in a direction which is anti-parallel to the ion beam. Okay, but you can also do the you can do a collinear version where you have a dye laser, and then of course you double and so on, and then you pass it like this, so it is moving along with the in the same direction as the beryllium 8 beam. So the result of this experiment is shown in the next slide. So you have, let's say, these 3 nuclei which have been for which spectra are plotted here, but this is done for 7, 9, 10 and 11. So 7 is not shown in this. So in the collinear spectroscopy you see a certain hyperfine or absorption spectrum in terms of a frequency relative to another frequency, the reference frequency. And you can see in the collinear case, it is this, you can see that these lines have this sort of structure, a strong line, then a weak line, and then 2 strong lines. Whereas this reverses if you do anti-collinear spectroscopy, okay, because this line actually then comes at a higher frequency, and similarly this comes at a lower frequency. Okay, so this pattern reverses. In an even case, you don't have such a structure, you just have one line, and whose of course frequency slightly shifts because collinear and linear, collinear and anti-collinear. Similarly, for 11 beryllium, a similar thing happens. These lines actually reverse, and you can use that to actually measure the nuclear charge radius. And so the nuclear charge radius is somewhat higher in the case of beryllium 7. It goes down to beryllium, in the case of beryllium 9, and is the smallest in the case of beryllium 10. But then it increases for beryllium 11. Okay, so so this is probably what is plotted for. This is probably some measurement, probably, but anyway, these are 3 measurements that agree. I don't exactly remember what this point was, but so let me see. Green, okay, the green is actually I think beryllium. Okay, beryllium 11, no doubt, but this is relates to some particular I think line. Okay, maybe in the I'll have to look at this aspect, but in any case you can see a systematic fall of the nuclear charge radius and then coming to a minimum and then rising. Okay, you also have magnetic dipole moments of each of these nuclei, apart from of course beryllium 10, which has a 0 spin and therefore no magnetic moment. So this also can be measured, and so the magnetic moment can be measured here, and it is indeed measured for beryllium 7, beryllium 9 and beryllium 11. Okay. So if you have, as I said already, if you have a muonic atom, and this you can get muons, mu minus as secondary beams from proton accelerators. So you produce pions, and then those pions decay and you can get muons, and then you can slow them down in absorbers and then get them captured in atoms. and they quickly cascade down to the lowest energy state, where they actually kind of replace the innermost electrons, because the muon is 200 times, as I said, heavier, and therefore it forms a very compact orbit around the nucleus of an atom, which is 200 times smaller than the K shell electron radius, and therefore it is more sensitive to nuclear charge distribution, to also to magnetic moments. But magnetic moments, the sensitivity is somewhat less, because the nuclear magnetic moment of a muon is 200 times smaller than that of an electron. So all these hyperfine splittings and so on are much smaller. However, it is more sensitive to the bound state energy, and so muonic X-rays have been used to extract this information. I don't have examples of it here. Maybe do that in some later date, or maybe as an additional slide or two, which I might add to these slides later on. Okay, so in summary, we have talked about the basic properties of nuclei in these two lectures, 18 and 19, and we have also discussed some of the techniques of measuring these properties. Thank you.